Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics and the chapters of mechanical actions, equilibrium of a body and Archimedes upthrust. This exercise was the previous one in the brevet exams in 2013 third session, third exercise. The title of this exercise is Roll of Rubber Rings. A buoy of mass m is equal to 42 kilograms. Then the mass is given in the SI. And of volume V is equal to 0.04 meter cube. Wants to swim in a swimming pool full of fresh water of density raw water is equal to 1000 kilogram per meter cube. So the boy is of mass 42 kilograms and his volume is given by 0.04 meter cube. Wants to swim in the pool having water of density 1000 kilogram per meter cube. Suppose that the boy is submitted only to two forces, weight of the boy W vector and Archimedes upthrust F vector, given that G is equal to 10 newtons per kilogram, which means that we are on the surface of Earth. So here let me clarify the following. So what does this weight represent since we have a liquid? Does it represent the real weight or the apparent weight? So whenever we are discussing forces, we are always interested in the real weight and not the apparent weight. Now number 1, buoy without rings, part 1. Show that the density of the buoy is ρ1 is equal to 1050 kilogram per meter cube. So in order to calculate the density of the buoy knowing his mass and knowing the volume, so the density, which is denoted by ρ1, is given by mass divided by volume. No need to construct a triangle for this formula because this is the quantity that we want. Now the mass is given by 42 and the volume is given by 0.04. Plugging this fraction on the calculator, then the density is given by 1050. Since both the mass and the volume are expressed in the SI, so the unit of the density will be in the SI, which is given by kilogram per meter cube. So the unit of the buoy is given, the density of the buoy is given by 1050 kilogram per meter cube. So let me write here that the density of the buoy, which is denoted by ρ1, is given by 1050 kilogram per meter cube. And now in number 2, deduce that the buoy cannot float on the surface of water, and by deduce it means that we need to use the part just previously before. In number 1 we have determined the density of the buoy, which is given by ρ1 is equal to 1050 kilogram per meter cube, and the density of the water is given by 1000 kilogram per meter cube. So in order to deduce that the buoy cannot float on the surface of water, we need to compare both densities, the density of the buoy to the density of water. And by compare, it means that we need to say whether ρ1 is greater than ρ water, equal or less than. Since they have the same unit, then ρ1 is greater than ρ. And whenever the density of the solid, here the solid represents the buoy, whenever the density of the solid is greater than the density of the liquid, which means that the solid is more dense, then in this case the buoy will sink, which means that he cannot float on the surface of water. So let's say since the density of the buoy is greater than the density of the water, then the buoy will sink. Which means he cannot float on the surface of water. Number 2, boy with rings. Part 1, the boy now passes his arms through two inflated rubber rings of negligible mass and of total volume V1 is equal to. So let me write here that V1 is equal to 0.0045 meter cube. So here this is important, that the two inflated rubber rings are of negligible mass and of total volume V1 given by this. So what does this represent? It represents the volume of the two inflated rubber rings. Let me make some space here. So we are in part 2, number 2, part 1, part A. Calculate the total volume V2 of the said boy plus rubber rings, and here by the total volume, so they mean the volume of the boy with the volume of the rubber ring. So by total it means that we must add them, so it is given by V plus V1. Now the value of V1 in the SI is given by 0.04, and the volume V1 is given by 0.0045. Now plugging this on the calculator, then the total volume V2 is given by 0.0445. Since both V and V1 are expressed in meter cube, then V2 will be expressed in meter cube, which is in the SI. Then the volume V2 is given by 0.0445 meter cube. We are in part B. Calculate the density ρ2 of the said boy plus rubber rings. So we are interested in determining the value ρ2, which corresponds to the density of the said boy plus rubber rings. So the density can be calculated using the mass divided by the volume. So what does this mass represent? It represents the mass of the boy plus rubber ring. And what does the volume V represent? It represents the volume of the boy plus rubber ring. Why? Because we are determining the density ρ2, which is given by the density of the boy plus rubber ring. Then the value of M must also correspond to the boy plus rubber ring, and the volume V2 must also correspond to the boy plus rubber ring. In part A, we have determined the total volume V2 corresponding to this set. It's left to determine the mass M2 corresponding to this set. So here, the value of M2 is given by, so what does M2 represent? It represents the mass of the boy plus rubber rings. So what is the mass of the boy? The mass of the boy is given by capital M. And the mass, let's denote the mass of the rubber rings to be M1. But here they are telling me that the two inflated rubber rings are of negligible mass. So now the value of M, which is given by 42, plus the value of M1 is 0, because the mass is negligible in this case. So the value of M2 is given by 42 kilograms. Now after we have determined the value of M2, now we can calculate the density ρ2, which is given by M2 divided by V2. The value of M2 is given by 42. And the value of V2 is given by 0.0445. Now plugging this fraction on the calculator, then the density ρ2 is given by 943.82. Since both M and V are expressed in the SI, so the value of ρ2 will be expressed in the SI, which is given by kilogram per meter cube. Then the density ρ2 corresponding for the said boy plus rubber rings is given by 943.82 kilogram per meter cube. Now part C, deduce that the boy with the rubber rings can float, and by deduce it means that we need to use the part just previously before. Let me make some space here. Now we are in part C of number 1 of part 2. And in part B, we have determined the density ρ2 corresponding to this set. In order to determine whether this set, which is given by the ball plus rubber rings, will sink or float, we need to compare this density of the set to the density of the liquid, which is given by water, 1000 kilogram per meter cube. Now in this case, the density of the solid, which is represented by the buoy and the rubber ring, is less than the density of water, which means that the solid in this case is less dense than water, and we know that whenever the solid is less dense than the liquid, in this case given by water, then the solid will float to the surface. Now let's say since the density of the set, between the brackets, the set represents the buoy plus rubber rings, is less than the density of water, then the set or the buoy will float. So let me write here also the buoy with the rubber rings. And now we are in number 2, part 2 of number 2. The buoy with the rubber rings is now at equilibrium. So now in this part we can use the condition of equilibrium at any time. Part A, write the vector relation between the two forces acting on the said buoy plus rubber rings. So how do you apply this condition? In other words, they are asking me about the condition of equilibrium. So as a title, we write at equilibrium. So always on the left we write the sum of forces acting on the solid on this solid, and they are given by the weight and F up thrust. Here I repeat that the solid represents the buoy plus the rubber rings, which is given by this set. Then W vector plus F vector. And on the other side of this equation we write the 0. We don't forget the vector corresponding for the condition of equilibrium. So moving F to the right hand side, W vector is equal to minus F vector. What does the first equation tells us? That the effect of both forces acting on this set cancel each other, whereas the second equation tells us that both forces have the same line of action, opposite direction, same magnitude. And recall that this weight represents the real weight, as we have stressed earlier in the beginning of the exercise. Now part B. Deduce the relation between the magnitude of these two forces, and by deduce it means that we need to use the previous parts in which we have determined the condition of equilibrium, which is given by W vector is equal to minus F vector. We are interested in the magnitude. So now we drop down the vectors. And we remove the minus sign. Then the magnitude is given by that W is equal to F. So this is the relation between the magnitudes. Now in part C, calculate the immersed volume V3 of the said buoy plus rubber rings. We know that the immersed volume can be calculated from the following formula, that the magnitude of F up thrust is equal to the density of the liquid times the volume of the immersed part times G. We are interested in determining the volume of the immersed part. So in order to determine the volume of the immersed part, we must know G, which is given to be 10 Newton per kilogram. We must know the density of the liquid, in this case is given by the density of water. And we need to determine the value of F up thrust. Yet till this moment we didn't determine the value of F up thrust, knowing that now in this case the buoy is floating at the surface of the liquid in which he is at equilibrium. So we can use this relation in order to determine the value of F. So knowing that W is given by F, but the value of W is given by M multiplied by G. So let me calculate the value of W here alone. So here what does W represent? It is the weight, it is the force exerted on the buoy plus rubber rings, and its magnitude can be determined using M multiplied by G. So because this force acts on the buoy plus rubber rings, then this M must correspond to the mass of buoy plus rubber rings, and we have denoted this mass to be the mass M2, and previously we have verified that the value of M2 is given by 42 kilograms because the buoy is of the rubber rings are of negligible mass. Then the value of M2, which is given by 42, multiplied by the value of G, which is given by 10. Plugging this on the calculator, then the value of W is given by 420. Since both M and G are expressed in the SI, so the value of W will be in the SI, which is in newtons. So the magnitude of the weight, which is the force exerted on the buoy plus the rubber rings due to Earth, is given by 420 newtons. Now, after we have determined the value of W, we can say that W is equal to F in magnitude, but the value of W is given by 420 newtons. Now, in this case, then, the value of F is given by 420 newtons. Recall that we are not interested in determining the value of F, however, we are interested in determining the immersed volume. Now, because we have determined the value of F, we are ready to determine the value of V3. Knowing that F upthrust is equal to the density of the liquid times the volume of the immersed times G. Now constructing the triangle of this formula. Here, because we have multiplied, and F upthrust will be at the top, rho, L, Vi, and G at the bottom. Knowing that we are interested in determining the value of Vi, which is denoted by V3. The F upthrust, so V3 is given by F upthrust divided by rho L multiplied by G. The value F upthrust is denoted by F. The density of the liquid is denoted by rho water multiplied by G. Now let's replace the values. The value of F is given by 420. And the value of the density of water is given by 1000. The value of G is given by 10. Plugging this fraction on the calculator, then the volume V3 is given by 0.042. Since everything is expressed in the SI, so the unit of V3 will be in the SI, which is meter cube. Then the volume of the immersed part corresponding to the set buoy plus rubber rings is given by 0.042 meter cube. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in a new one.